For this question, we have a monochromatic light, right, passing through diffraction grating. You see the pattern is as such. Monochromatic, right, means only one wavelength. Okay, therefore, right, the pattern is only like one line. Yeah. Next, right, we know from the diffraction equation, right, diffraction grating equation, d sine theta equals to n lambda. In this case, we are seeing the first order, so n is equals to 1. Yeah, so here, right, it tells us that the further away from the center, the larger the wavelength. Okay, so this gap here, right, represents the lambda. Okay, so this tells us, right, this is a particular frequency, particular wavelength. Now we are passing this particular light through a cool gas. Okay, so this is the light source, passing it through a gas, and we're going to analyze from here. Okay, yeah, and so what's going to happen? Well, this light, right, is absorbed by this gas, and this gas, right, we do not know the energy structure. Okay, energy level diagram. So, but let's just deduce in a logical way. So once again, let me draw in a free state first. So let's say that this is the ground state of the gas. Okay, and this particular monochromatic light, right, managed to excite this gas all the way up to this level. Okay, now we do not know the energy level diagram of this gas, but we could guess, right, there could be maybe some levels here, some level here. Of course, there could be levels above, but those are not within our concern, because these gas molecules, right, can't go higher than what the light can bring them to. So we are concerned with, right, the possible lines which are beneath this excited state that we are talking about. So what are the possible de-excitation that can take place? Well, if this guy, right, managed to go up, he can drop here, drop here, drop here, or drop here. Okay, so what are we sure of? Well, one of the possible transition, right, is re-emit back the same wavelength, okay, as the one, right, that strikes it. That will mean, right, that we should expect the original wavelength, right, to be still visible. So that will be this one. Can there be any wavelength, right, which is smaller than this particular one? Not possible, because, right, that is the highest that you have brought this atom up to. Therefore, right, these are not possible. Could there be wavelength which are smaller, wavelength which are larger, which correspond to smaller transitions? Possible, because that will correspond to the excited states underneath the one that we are concerned about. So these are possible. So answer will be C.